you have any idea how to tackle C and D? If you don't, that's okay. Do A and B, because I'm going to be doing it too. If you don't, okay, do A and B. That's old school, that's review. Let's start at C and D and be like, do I know how to do that? Just take a couple minutes. If you do, go for it. If you don't, that's okay. Go back to A. Okay, Harry, so I need you to please. Yes, on part C, if you guys haven't been able to start it yet, think multiplying both sides by a dx. If you haven't been able to do it yet, think multiplying both sides by a dx. Think multiplying both sides by a dx. For those of you guys in the video, just in case you missed what we're doing, we're in example number 14 in our notes slope field packet. Kind of in preparation for you guys trying to finish this up tonight. Not this as in the notes packet, but as in the homework packet that you have. Trying to face a couple different directions with slope fields that we haven't seen yet, or I should say differential equations that we haven't seen yet. So they're on example 14 in the notes packet. Specifically trying C and D, unless they don't know how to do that, then they are going back to A and B. discuss in your groups real quick. Maybe not what you were able to finish, but what you were starting, what you were thinking, what you were pondering. What the second derivative is supposed to tell you, how you were supposed to find it. What letter C was asking.
That would be sad if I didn't do it.
How is it 0 when it's right here? Because if it was number over 0, then it would be. No way.
All right, let's see how you guys are able to do. Our next book work isn't due until Thursday. That kind of helps a little bit as far as giving us a little bit more spread of time. Today we're able to take some of this time on slope fields. I still want to introduce section 5.2, so have your notes close. But it's okay that we're spending a little more time on slope fields. So, if you guys were to have done the slope field, which maybe some of you had no clue on C and D, so you just came back and you made the slope field. But maybe you didn't know what you were doing, so you didn't even touch it. Just remind me really fast, like, how do we actually make a slope field? And for some of you, that's exactly where your homework packet starts, right? Is making lots of slope fields and practicing. So real quick, just to make sure that we can. What do I think through when I actually go making baby tangents? If you were to teach me how to do it, I had no clue. I was a calculus kid, so I kind of like done all this stuff, but I missed all week last week. What would you tell me? Sure, and then do what with 0, 0? Okay, so when we plug in 0, 0, we're going to have 0 over 1, which is 0. So now what? That I know dy dx is 0.
Slope is 0.
Slope is 0, okay. Where else is slope 0? Y up and down. Anytime x is 0, and what kind of line is x equals 0? When x equals 0, think tick marks on the x-axis. X equals 0 is technically a vertical line, so x equals 0 is going to travel all the way up and down. 0, 0, 0, 1, 0, 2, 0, 3. So what can I do with all of those? Well, yeah, what was the hint about when the slopes travel or are parallel and vertical lines? When the differential equation is only in terms of x. So how do I move to the next vertical line? I think about what is x equal to? X is equal to 1. So what happens when I plug in 1? 2 over 2, which reduces to b. Now, what do I do? You guys teach me. What do I do if dy dx is equal to 1? Oh, so up 1 over 1? And then I just connect it?
No.
With a little baby, yeah? And then I make them parallel. Okay, what happens if I go to 2? 4 over 5. Ah! What would your advice be if I try to do 4 over 5? 1, 2, 3.
Still do it.
Still do it? What would 4/5 be in relationship to 1?
Pretty close, a little less.
A little less. Is it okay if we just go a little less?
Yeah.
Sweet. Probably should have gone a little bit steeper. That was a little 4/5. Is that cool? What happens if I go to 3?
6 over 10, which is
Almost like a half-ish, right? So that'd be like
3/5.
up 1 over. That's up 1 over 1. Sorry. Up 1 over 2. There we go. It's even less. But what happens when I go to the negatives? How about -1? Because I'd have -2 over 1 plus 1 is 2, so y is already like, hey, I've already figured it out, it'd be -1. So then negative, wait, how do I do that rise over run again?
Wait, it's just flipped. It's just flipped.
Yeah, flipped, or you can think downhill, or you can think, remember, go down 1 over 1, right? So we just have that all be parallel. Any ideas what -2 is going to be? Yeah, -4/5, so that one just a little bit. Just flipped as in downhill instead. And then -3 would be the same thing, almost a half-ish. So 1, 2, there we go. Okay, that was part A. What do we do with part B if it were to ever ask for a solution curve? And why am I getting out a blue pen? Sure. 0, 1 establishes a point, right? And when I establish a point, what is my job to do if I'm trying to sketch the solution curve? Go with the flow, follow the flow. Does it make sense why I'm going to be on top of that tangent line? Because I'm skimming it, right? The tangent line is supposed to skim my curve. But then do you guys see how? Ooh. Is it getting less steep? Just a little weird. Do you see it?
Looks like a wave. Looks like a
Yeah,
black
kind of.
hole.
Kind of, huh? Okay. Some sort of practice. Anyway. Does yours have to perfectly go in between the exact same baby tangents that mine did? No. Does it have to be generally following the flow, though, of being steep and then getting less steep, and then having negative slopes and getting less steep? Yeah, it should somewhat. Okay, that was A, that was B, that was kind of review. Hold on really quickly. If you have your homework packet out, are you going to be showing the flow in any of those, the 6?
Yeah.
Any of those 6
No.
problems? No, because all they give you are
Just
the equation of, careful, be specific.
derivative.
Otherwise known as the differential equation, right? So they've only given you the differential equation. What else would they have to give you for you to follow the flow? A clue. They'd have to give you a point to establish it, right? So if they give you a differential equation, we can make the baby tangents. We can see all the flows, but we're not going to be actually marking the flows. However, can you look in that homework packet and find me a place where you will be sketching the flow? You've probably seen like multiple choice.
18.
Ooh.
17.
17, 18, you're starting to see them giving points and then asking you to sketch a solution curve, right?
Asking questions based on that.
All right, so let's come back to our FRQ and see what's going on with C and D, because you just started seeing places where you will be sketching the flow, but when you guys found those, didn't you also find other parts to that problem? Okay, letter C, how do the directions change? Oh, sorry, did I say C? B said sketch the solution curve, follow the flow, we did it. What does C say? Find the solution curve. That is the new step of solve. And specifically, usually when the AP says this, it says solve for y equals f of x. Usually when it wants you to find the particular solution for your curve, and they haven't already given you, we saw last week them saying like, hey, verify that y equals something like cx cubed is a solution curve. Like, oh, I just have to plug it in and make sure it works to my differential equation. And then it said to find it given a clue, but this one says, no, I'm not telling you what it is. I'm just giving you the differential equation. How do we go from a differential? Okay, tangent line, sketch the solution, but how do we go from the differential to the equation of the solution? Anti-derived, good. But we have to do that legally, so careful. Did you remember, or did you hear me when I said what the first step should be? Multiply dx. What happens as soon as I multiply dx? What does this almost look like? Okay, yeah, you said, but what kind of problem? What's missing from this? An integral, yeah. So throw an integral on both sides and be like, ha-ha, now I have my bookends. What I do to one side, I can do to the other. I can derive both sides. I can integrate both sides. So throw an integral in there, and then some of you were like, hey, u sub, is this arctangent, or is it like ln? Why is it ln? ln is 1 over u versus 1 over u squared plus a squared. It could have been a u squared plus a squared, but what are Wyatt and I seeing up here?
2x.
Which is my du, right? So I can make it the ln because that's what's going to fit naturally. Arctan, if it was 2 over, arctan's perfect. It's the way I would have had to have gone. But it's 2x over, which is perfect because check it, isn't 2x my du? You still have to show all your steps. Go ahead and do it. When you guys plugged in, Chuck, did you notice that the 2x reduced away and you just got 1 over u du?
Yeah.
Technically over here, the integral of 1 is y. You could say y plus c1, but in just a second, you're about to get another plus c, and so the c1 and the c2 could combine to be a don't think. Why am I putting a parenthesis around ln of u, which is x squared plus 1, instead of absolute values? Even though the formula is technically ln of absolute value.
Because x squared is never going to be negative.
X squared plus 1 will never be negative, it's redundant. Now wait a minute, am I done? No. That test you guys recently did corrections on, if you stopped there, you would have been in trouble because there has been given to you a, and what does a clue do? Establish a particular solution. This is the general solution, plus C, I don't know what C is. But the particular solution says, you should be able to find it, right? So we bring down our clue and we say, okay, hold on, wait. We know because of the point 0, 1 that 1, the y value, is going to equal ln of 0 squared plus 1 plus c. Well, wait a minute, guys. What's ln of 1?
0.
Ha! So what's c equal to?
1.
Is that my solution?
Combine them and then.
Combine them and then it is. Remember, the solution is a curve. The solution is a function. The solution is this guy, ln of x squared plus 1, with the c plugged in. Question, if we had more time, could we get out our nifty-difty graphing calculator and graph this and see that it looks pretty close to that? How does it look pretty close to that? Wait, ln has an asymptote, right? That's only if this guy goes 0 or negative. Didn't you just say he's always stuck being positive? His domain is all real numbers. He's kind of like an ln, but because of that x squared plus 1 expression, he's not going to have an asymptote. Anyway.
Whoa.
What's going on in part D? That got interesting. All of a sudden it started talking about deriving a derivative. So differential equations, we can make slope fields out of them. We can integrate them sometimes. Sometimes it's impossible. We can use them, or we can even derive them. Do you guys take a derivative of a derivative with a quotient rule?
Mm-hmm.
Because wouldn't you have to take the derivative of dy dx in order to get d squared y over dx squared? But what you do to one side, you got to do to the other. Good old school algebraic thinking, right? Boop, boop. So then bottom to top, you guys end up with x squared plus 1 times 2 minus, do you remember your quotient rule? Top, you haven't done them in a while. D bottom, whoops.
Actually, it's stuck in there.
What's the derivative of the bottom? All over bottom squared. Did you not kill some poor unsuspecting kitten? You did not cancel out something that was only in one expression but not the other, but instead you legally simplified and got your 2x squared minus 4x squared is negative 2x squared plus 2 all over x squared plus 1 squared. Did you still not kill anything and properly factor out to see if they matched before you started reducing?
There you go.
Can anything reduce? Absolutely not. That doesn't match this, and this doesn't match that. This factors to be x plus 1, x minus 1. This does not. It's imaginary. It's always positive, can never be 0. Square root of a negative number is I. Not me, but I. Wait a minute. What's this actually asking for? After you find d squared y? P.S. If they ever tell you to find something, you're getting points for it. Do it carefully. Do it legally. Wait. Could you have technically, in an FRQ, stopped here? No. Stick it to the man, you could have stopped there, but what's the problem about the rest of the question?
What do you have to find CalcAB?
Concave up and concave down. So here's the dilemma. Even though you could have stuck it to the man here, wouldn't you have to simplify to get your pips to make a sign chart for the second derivative of Tesla? It's a bummer. It's true. You could have boxed this. You could have kind of, since this guy's always positive, set this guy greater than 0, set this guy less than 0, and never simplified. It's just, I don't know. And this is one of the cases, because I have to use it, I probably would have simplified, just because right now my life is so much better if I realize that, oh, hey, got him. Domain, all real numbers. I have actually sign chart. It doesn't count as justification. So I'm actually going to make him little and off to the side, because he can't be my justification. He can just kind of be like my scratch work. Second derivative, I need f double prime. Why did I choose -1 and 1? Isn't it kind of obvious? Right? If I go ahead and plug in 0, a negative times a negative is a positive, which means I have concave up. If I plug in 2, that's going to be a negative, concave down. And if I plug in like a -2, still going to be a negative. Oops, wrong way. So concave down. So therefore, I can say, since d squared y all over dx squared is less than 0 on both negative infinity to -1 and 1 to infinity, y equals f of x is concave down on those intervals. You guys see how I'm just taking my sign chart and making a sentence out of it? Right? And so then you guys, your turn. How do you finish it?
D squared y x squared is greater than 0 on -1.
Why am I not closing those brackets? Are you closing them? Yeah, because these are equal to 0, not negative or positive, right? Okay, keep going, Kyle.
Y equals f of x is cu on that.
Could you write out concave up? Yes, of course you could, but I'm just being lazy. Do you guys see how basically I just stole their wording as far as like, hey, you want the concavity of this dude? Sure, I'll talk about the concavity of that dude. You want the intervals? Sure, I'll talk about the intervals. And then I'm just using my forever card, basically, saying like, hey, this is what the sign chart told me. Got it. Is that cool? All right, so what are you going to face in this packet when you're trying to finish it up tonight, tomorrow, collaborating in groups for like 5 minutes, and then tomorrow night, if you still need to, maybe even 0 period Wednesday morning. You're going to have to read carefully the directions. They're going to always give you a differential equation. Sometimes you can actually find it by hand. That's this part C. But if you guys are one of those like highlighting, warning type AP-ish, what could come, just remember that this is only sometimes possible. And this one, it totally was. Sometimes possible. Can I show you one where it wouldn't have been possible? Is one of those that we skipped. Can we just go to example number, well, actually, could have been almost any of the other ones. Nope, 13 was possible. Example 11 and 12, nope. 11 is possible. Okay, just kidding, 12. I thought there was another one, but maybe it's number 15. No, 15 is possible. Oh, 16. 16, he's one of those diagonal guys. He's one of those plus or minus guys. This one we can't solve for y equals f of x. So no matter how they word the question, no matter how much it sounds like we're supposed to be solving for, unless they give us a form of the solution, we don't know how to find it. We're not able to take an integral of that. You are not able to take an integral of that, and you will not be able to by the AP 10. And just so you guys know, easy can't either. This one is another one that you can't solve for y equals f of x. Unless they give you like a form, unless they give you a, hey, this is a solution, so now work with it. we can't actually do what was just asked of us. All the other ones you can. As long as it's multiplying or dividing, you can. But as soon as you start having these diagonal guides, this addition or the subtraction of x's and y's, there is no way to properly split it up. We'll learn more about that in section 5.3. So we're not going to spend a lot of time on those two right now and why it's not possible. Just letting you know there are a couple that, even though some FRQs are going to ask you for this take an integral step, this is only sometimes possible. So sometimes it's going to sound like they're telling you to, or it's going to sound really similar, but they're actually asking you to use it or to deduce some information from it, because it might be impossible to do this step. Anyway, just throwing it out there. We'll come back to that for sure. But for right now, let's go ahead and put away the slope packet. I want you guys to be able to see the evens from last night's homework for the book work, just in case. Oh, wow, we are not in chapter 4B. What am I thinking? Aren't we in chapter like 5? And as I'm getting that homework out and ready, because I had, I had the wrong chapter ready. Let me get you guys at least, ooh, my bad, hold on, this isn't 9.3, this is, where are we at? 5.2, my bad. I know. Chapter 9 was another book, believe it or not. It was chapter 9 in another book. I'm going to have you guys start taking notes, because remember, we did need to at least introduce the next section. So I'm going to go ahead and get your evens up, because I totally had the wrong chapter. I apologize. We are not going to have to worry about a handout for this section, just because our book does a good job of covering it. An old book that we had did not do such a great job, so I kind of had to supplement. But our book does a good job, so we're just going to use some examples. There we go. All right, let me freeze the screen so you guys can start on the notes. Thanks for getting your homework ready. Let me go get the answers ready. Just needed to get notes started, so we're going to be able to do that. I think we'll probably go over homework questions tomorrow, homework and packet questions for those of you that have gone through the packet. Hopefully avoiding that on Wednesday so we can work predominantly on this section on Wednesday. So have questions ready for me for tomorrow. We'll get to peek at those evens in just a moment on the book work. But guys, hopefully when I write this down, you're like, oh yeah, duh, you've been saying it for the last week. dy dx, those are differentials, right? Implying differentiation has occurred, right? If we see something like solve the differential equation, which we just did, but the one that we just did had everything ready to go as it was, 2x over x squared plus 1, all we had to do was move the dx. It's a little bit different when we have something with x's and y's, an expression or a differential equation in terms of x's and y's. Because if I go rewriting this, dy dx is equal to 2x over y, and if I go moving dx to the other side, am I able to integrate right now? Throw in an integral, it's ready to go. No, because I can only integrate expressions in terms of x on this side. But wait, what is t allowed to integrate over here? Expressions in terms of y. So what should I do with this guy? Since he doesn't belong on this side, I need to multiply him over to the other side. So you're going to start to see in these harder differential equations, the name of the game is, can you get everything in its proper place? dy can integrate y's, dx can integrate x or x expressions. So if I just do one extra step, all right, now let's go. So we do have this little 2x squared over 2, 2's reduced. X squared plus like a c2. This one could be a 1/2 y squared plus a c1, but we move that c to the other side. But all of a sudden, life just got a little bit harder. It didn't really. Life has always been complicated, but you guys have been exposed to a harder type of differential equation where it's not just y equals the integral of the other side. This time it's y 1/2 y squared equals. So if I multiply both sides by 2, that 2 can multiply to the x squared. It can multiply to the c, what would that be now? 3 times 2 would be c4, but whatever, we'll just absorb it. But now we have y squared. Well, wait a minute, hold on. y squared, if I square root that, I get a plus or minus square root. So this is one of those, remember how I had you put your finger on Saudi Arabia, and then I ran and followed the wind and how it was different? All of a sudden, I just realized you can get more than one type of solution out of a differential equation depending on the math that's done. Do you also see how the plus c is stuck under the square root? I can't just write them outside. That's illegal. I can say 2 times c is c. I can say c1 and c2 is c3, but I can't just randomly put a plus c. He's stuck now under the square root. And also, this is going to be behaving sometimes like a positive root and sometimes like a negative root. Depending on the points. Anyways, we're going to talk a little bit more about this starting tomorrow. And section 5.2 isn't handling all types of differential equations. It's getting specifically into exponential growth and decay. And my chemistry people, we're going to be talking about half-life and doubling. But section 5.2 is a very special, a very specific, a very particular application of differential equations, exponential growth and decay. And then 5.3 says, okay, but hold on. There's a lot of different types of growth. There's a lot of different types of differential equations. Let's not get stuck in this 5.2. Let's broaden our perspective. And the AP rarely gives you something as special, as particular as 5.2. So we're going to kind of camp out here because it's important for the sciences. But then 5.3 says, okay, pause, time, zoom out. Let's just be seeing these differential equations in general. So we'll come back to this tomorrow as far as what happens for these two very special types of differential equation, how we have the rate proportional to the amount, or the opposite amount, the negative amount. We'll come back to that, but for right now, I know we're going to run out of time. I'm going to go ahead, though, guys, in the end of today's video. What am I doing right now as I'm still recording and having you guys pack up?
Showing us
Showing you and showing anyone who watches the video tonight the evens. So what could you do? Grade the evens, come tomorrow's questions. Sound good? All right, get out of here. Chapel day. Be excited. Be praying for your teachers that are talking and sharing with you guys today. I'll see you guys later.